Well, good morning, gentlemen. Interesting, just a couple of general points before we start. When there's a new study design, any course, but any study design, anyone who presents material to you is giving their interpretation of study design. Your teachers are, I am, your tutor if you have a tutor made, any sessions you go to. There's only one interpretation that really matters, and that's the interpretation of the chair of the exam panel. They're the ones who set the questions. Where does that leave us, this being a new study design with past history? Well, generally speaking, about 80 to 90% of the questions on past exams are still very relevant. It's almost a different style, a different emphasis. And the thing about questions on past exams is they are history. They are a history, and the assessment reports for all those exams don't just tell you the answers to the questions, they give you a breakdown of student performance. And that's really useful to see, because accepting the fact that we expect this to be a pretty strong cohort, certainly at the upper end overall of chemistry in Victoria, even at the top end, there are questions that can prove challenging. There's the odd question, for example, that maybe only 5 to 10% of students get full marks on. There's the odd multiple choice question that only 30% of students get right. Now, for those of you, which I presume will be many of you, aspiring to be in that really, really top echelon, there is still a lot to learn from what was it that challenged students in the past. Because the day can come when you're sitting in the exam being extremely well prepared and sitting there thinking, this is odd, this is different. I haven't seen anything quite like this before. Now, of course, if you're well prepared, it's pretty much guaranteed that the other 10,000 students doing chemistry at the same time are feeling the same thing. Some will give up if it looks different. Others will persist and say, I've got the knowledge base, therefore I can work this out. And that's what you've got to keep in mind. So with that in mind, it is interesting to, now don't copy this list out, it may not be accurate. There basically refers to questions on past exams. But that website, which is the CEA website, gives you an unofficial indication of questions from past exams that are still relevant. What I've listed there are the ones that are not relevant on the left, and that's only my quick look, so I don't guarantee that as gospel. But it's interesting, you'll notice, for example, on the 2012 November exam, only one question in Section A and a few parts of one question in Section B are considered not still relevant. So that really gives you a good insight into at least an understanding of how to do questions or how students in the past have performed. So when we actually look at, and I'm not going to read through the study design, in your notes, you've probably had it anyway, I've just given you the key components of the study design. Now, it's just like, I just thought I'd stop on one. The comparison of fossil fuels and biofuels with reference to energy content, renewability, environmental impacts. That's sort of like what we might call motherhood and apple pie stuff. It's pretty obvious stuff. You know what coal seam gas and petroleum gas and crude oil, effectively alkanes, coal mainly carbon, and then you of course have all the issues with CO2, you have the issue with non-renewability of fossil fuels, etc., etc. And I wondered whether an examiner might be a bit intuitive this year and say, well, look, why don't we give them something on clean coal as an interpretive exercise? And what is clean coal? Clean coal's not specifically something you have to study, but all it is really is carbon capture in the sense of trying to ensure you capture CO2. Now, I'm not saying there's something you have to know. It's not mentioned in the study design. Doesn't mean you couldn't have a reference to it as long as you were given material to interpret from. And petrodiesel and biodiesel. It's a good idea to know the difference between petrodiesel and biodiesel, and then the other things like viscosity, hygroscopic properties, etc., environmental impacts. they sort of they follow fairly logically. Biodiesel does or does it not have an environmental impact? That's a point I'll come up again later in one of the questions. Then we just go on, slide after slide of the key knowledge. Now you can just go through all these slides at some stage and say, yeah, covered that, covered the stuff on the extent of chemical reactions, Le Chatelier's principle, done the production of chemicals by electrolysis, done rechargeable batteries, then Unit 4, all the organic chemistry stuff. And this is just a very quick reminder of what the course is. But I'm going to stop here. Structure and nomenclature of organic compounds. I'm not quite sure I understand why they did this. Look at the second and third dot points. In the structures, you are meant to understand or recognise the structures of alkanes, alkynes, benzene, haloalkanes, primary amines, primary amines and amides, etc. But when it comes to naming, a lot of those aren't mentioned. There's nothing that says you have to be able to name aldehydes or ketones. You probably can, but it's just, strictly speaking, according to the study design, you cannot be asked to name an aldehyde or a ketone. That's just my interpretation. That's my interpretation. Is it the right one? I guess we'll find out on November the 14th, is it? The second Tuesday, anyway. And then all the other stuff on organic compounds analysis. It's a massive, it looks like a massive amount of work. And I just put the slides in there to remind you. Now, you probably can't see the highlights in black and white. If you do want to get hold of those highlighted slides, see Miss Cassidy, she's got the coloured version of it. So let's move, and of course area of study 3. This is the last part of, listed as the last part of Unit 4, but you may have studied it in Unit 3. School bells. Now, wonderful things, aren't they? Now, this key knowledge, you've been assessed on your practical investigation. Can you be asked about it on the exam? Yes, but not your practical investigation. An investigation where you're given a scenario, you're given data, and you're asked to interpret it. There's been questions like that on recent exams. But things like independent, dependent and controlled variables, obviously they're fairly easy to ask on an exam. But the specifics of that area of study, I would say there will be a question on the exam which will be a throwback to that, but not a specific investigation, but your ability to interpret the data given, criticise the procedure, suggest ways of improving, identify controlled, independent, dependent variables, etc., based on material you read. So, I thought I'd throw in a question that's not on your slide to start with, a bit of atom economy, a little bit of clear thinking for you, a bit of a challenge. It's a nasty little question. Basically, you should have an idea of the formula of fructose, since it's an isomer of glucose, which therefore you know its molecular formula. You can work out the molecular formula of levulinic acid, which means you probably don't need to do much else in terms of working out the atom economy. But the point is, it's nice to look at the other formula as well and interpret it. So let's see what the equation might look like. Good idea to turn this. Don't tell me it's not going to work. There we go. Do you agree with that as a semi-structural formula of levulinic acid? What have I done there? Oh, here we go, yes. Working from right to left. You agree with that as a semi-structural formula? Therefore it's molecular formula. You know fructose. So you should be able to work out what X is based on that information, just as a matter of logical interpretation of chemistry, atom economy, atom count. So we basically get that X is CH2O2, which is, it's actually methanoic acid. That's just a little bit of a fiddle with, yeah, we know what the equation is, we can work out the formula of compound X. Just means we need to know the formula for fructose and the formula for levulinic acid. Then your atom economy, basically it's just the mass of desired product over total mass of products. And again, I'm not going to labour on this, and it should work out to be 64%. Does that ring a bell? Good. That was just a general bit of get the brain turned on, look at a few things differently. Now we get serious. So, and if you get an answer for 62. Now, some of these questions are original, so if you notice a typo, please let me know. In fact, a lot of these questions are originals. It's a new course. So let's get right in. Question 1. Nice bit of stuff on food chemistry and all sorts of bits and pieces. It goes everywhere, this question. Going to occupy us for the best part of 20 minutes. Have a quick look through the whole question. Don't just stop and do part A. Read the whole question first. Because there's a lot in it. It's going to develop a lot of stuff for us. So remember, this is my interpretation. Read the whole question so you can see the pattern behind it. I can't give you time to do the whole question because it will take a lot of time, but think through how you would answer the various parts. And we'll pick it apart. Because it's going to develop into other things, not just the answers. So I've all read the whole question. I'll go relative, you should be able to keep up with me on this. Types of biomolecule, fairly straightforward, I hope. We're going to do parts A and B. The types are proteins, triglycerides, starch, polysaccharides. Polysaccharides probably, so any of those will do in that sense. Yes? Yeah, polypeptide protein, yes. Yep. I can accept that. Prefer protein, that's all right. Identify a chiral carbon on each structure. Ugh, chiral carbons. Aren't they just simply carbons that are bonded to 4 different things? So that's not, I mean, chiral carbons are not a difficult concept. Of course, it just means your molecules have non-superimposed mirrors. How about, concern? How about that one? Here's a quick question for you. What's the only amino acid that does not have a chiral carbon? Glycine. CH2. Glycine. Nice little tricky exam question. That's pretty obvious, but... And what about that one for triglycerides? This emphasises a good point. It's not just... It's like NMR spectroscopy. It's not just the atoms to which it is directly bonded. It's the whole group. So this is clearly a different bonding group than that group, and then you've got the hydrogen and the bit in the middle. And of course in NMR spectroscopy we know that to have the same environment, the atoms must have identical groupings. Get back to that later. Starch and polysaccharides, usually that carbon there in the ring is the one which stands up nicely as a chiral carbon. Describe the functional group changes that occur in the hydrolytic digestion reactions of these biomolecules. Quick mental check. Functional group changes. Changes. What to what, what to what, and what to what. Good revision point. We know the functional groups present in the molecule are obviously your starting point. So let's look at that one. Oh, we've already done that. So, functional group changes. We start with and all digestion products doing 2 parts. So we have the peptide group going to carboxyl and amino, a group. We have the ester group going to carboxyl and hydroxyl, and of course the glycosidic link going to, or ether group going to hydroxyl. Name the products. This is where your data book comes in handy. So your products, the 3 amino acid structures can be deduced reasonably good. This, by the way, no need to copy this down, it's in the answers as it looks here. But you should be able to identify the 3 amino acids: alanine, glycine and aspartic acid. That's basically just starting there with alanine, glycine and aspartic acid down the end here. So basically going around through those peptide groups. And of course, when you break up your fats, you get glycerol and the 3 fatty acids. And those 3 fatty acids, the fatty acid is just CH3, CH2, 16, COOH. So that's turned into COOH, that into OH. And your 3 fatty acids are stearic, linoleic and linolenic, all of which can be named because they're in the data book. Now, of course, what about these fatty acids? What else do we know? We'll get there in a moment. Because when we digest the starch or that simple polysaccharide, we end up with glucose, of course. Now, a little bit more on the fatty acids. Stearic acid is saturated. Linoleic acid is polyunsaturated. There's 2 CC carbon double bonds. Linolenic acid is also polyunsaturated. There's 3 CC carbon double bonds, CH-CH. We can add another classification there. Linoleic acid is an omega-6 fatty acid, because going from the non-carboxyl end of the molecule, the carbon-carbon double bond starts at carbon-6. And linolenic acid is an omega-3 fatty acid, because it starts at carbon-3. So all in that one question, we've got lots of bits of stuff which are relevant. Moving on. We come to the products of digestion of one of the molecules have the same functional group but different structural features. I think we've just answered that when we talked about the fats. Now, of course, you like that one? Just which I put more of those in now, didn't realise they were so entertaining. Now, so looking at the line structures of the fatty acid, stearic, saturated, 18-0 means 18 carbon, no carbon-carbon double bonds. Then you've got your linoleic acid, 18-2, 2 carbon-carbon double bonds, and omega-6. And then linolenic acid. Now, interestingly, we look at the stearic acid actually has the highest melting temperature because you don't have the kinks in the chain, which means the molecules can pack together more readily and therefore are harder to separate. And then we look at the idea of the cis fat molecule as you get the trans fat molecule. In the cis one, both hydrogens bonded to the carbon-carbon are on the same side, and both carbon groups are on the opposite side, obviously. And the trans, you actually have the hydrogens on opposite sides of the carbon-carbon double bond. And so you actually have the trans actually has the higher melting temperature. It's easier for trans molecules to pack together than it is for cis, because they don't have that massive kink. Now, oleic acid, where it's nice little monounsaturated as a version. There's another version of oleic acid called oleic acid, which is actually, it's a cis versus trans option. You'll get this slide. And so basically, the cis version has a lower melting temperature than the trans version. And that cis, that kink in the cis is far more pronounced, has a far greater effect. You've got everything on that slide in your solutions, if that's a useful reminder. So I'm not going to spend a lot of time. Oh, well, that was even better. I ran out of patience after a while. And basically, trans molecules pack together better because you've got better dispersion force attraction as a consequence. And that's in your solutions as well. There's the idea of the cis versus trans. Now we come to F. Now this takes us into a lot of territory. One of the structures belongs to a group of biomolecules that have 4 levels of structure. Identify these levels and the main associated bond types. Now you should be fairly up to date on that. Proteins obviously. And so we look at the primary, secondary, tertiary, quaternary. It's a nice little Pearson education. Please don't let them know I do this, they'll probably sue me. Now, and again, that looks familiar, and we'll go into a little bit more detail. The primary structure, effectively held together by the covalent bonds in the peptide link between carbon and nitrogen. Secondary structure is where you've got your basically hydrogen bonds between peptide groups on different parts of the chain. And the hydrogen bond is specifically between the hydrogen on one group and the oxygen on the other. That's it. Everyone knows it's hydrogen bonds. If you're asked to describe the bonding in the secondary structure, I don't think hydrogen bonding is enough of an answer. If you're asked to identify the type of bonding, I agree. But to describe the bonding, is hydrogen bonding between the hydrogen on one peptide group and the oxygen on another peptide group. That's subtle distinction, which you see from looking at past exam questions. What's the difference between identify and describe? I hope that's a good example of the difference. And then we have the tertiary structure, which is where you get all sorts of fun and games. Ionic links, sulfur-sulfur links, more dispersion forces, even hydrogen bonding. And you actually have bonds between the side groups which come into play then. And then the quaternary structure, which is like a loose aggregation of a number of protein chains. Not massively strongly bonded, a fairly loose aggregation, and certainly non-covalently bonded. And of course, a good example of that is certain of these, like hemoglobin, actually has iron in the molecule. Now, iron actually links us then through to cofactors and coenzymes, which we'll get to in a moment. So, again, hopefully that's a reminder of the 4 levels and the associated bonding. That's really all I wanted it to be. So we push on. Oh, no, I just like that. Don't know where I picked this one from. But again, it's just to look at, say that sort of makes sense. The primary, secondary, tertiary, quaternary. And it shows that basically that idea of the quaternary, that packing of 4 different groups in hemoglobin, or 4 different protein chains in hemoglobin. Nice structure. Moving on. This is an interesting question. It appeared on an exam. And I reckon it's this very poorly worded question. I'll explain why. You decide on your answer. This is the sort of question that creates conundrums, or even conundra, for people deciding on marking cards. Now, interesting question. Now, I'm going to argue for 2 answers, which is this range. Firstly, you made a decision. Let's presume you have. Tertiary only. What? How do we decide on tertiary only? Well, this is just it. I'm not saying that's the actual answer. At 25 degrees, there may be minimal effect on the secondary structure at low pH. Problem is, we don't know. It says a dilute acid. Is it a dilute strong acid or a dilute weak acid? So, possible answer. The tertiary structure will definitely be disrupted because the H plus ions interfere with the basic ionic side groups. So basically that's an argument for D. Hydrogen bonding can be disrupted by a change on pH. Maybe the effect of a dilute acid is unlikely to impact all that stuff. That's D is the answer, then there's also B is the answer. Which again, the way the question was worded, you'd have to accept B. Because you don't really know the effect of pH on hydrogen bonding. It might. We don't know what the acid is. We don't know if it's a strong acid or a weak acid. It actually, the is likely to be disrupted. We know the tertiary will definitely be disrupted. It's just a badly worded question. You'd prefer, I guess, on an exam, you'd almost be put in a situation of accepting B and D if it appeared to here. But there's a little bit there. We know how the tertiary structure is impacted. The H plus ions can basically affect side groups, cause protonation of COO minus or NH2, disrupt ionic bonds. Hydrogen bonding may, depending on the acid, also be disrupted. So the secondary structure might be disrupted. Hence that makes B the better answer in that sense, because of the might. We just don't know. We just don't know. That's why multiple choice questions. Now that question would be interesting. What they would actually be interesting to see how the students would respond on that. Who would have chosen B? Who would have chosen C initially? So the A would have won B. But it wasn't a great question. The might, there's no guarantee that a very dilute acid at a low temperature will disrupt the secondary structure. We don't know. You need more evidence. So I would have accepted B anyway. So that's great, you know. But moving on. Enzymes. All that stuff on enzymes which you don't need me to read through now. You've got that slide. Whether you need to know about proteases and bases. But denaturation is an interesting one. See, the disruption of secondary structures is really it's irrelevant in a way. Because once your tertiary structure is disrupted, the enzyme can work effectively. And the tertiary structure is the key. So you're probably unlikely to break down the secondary structure if the tertiary structure doesn't first break down. So the active site is not maintained due to denaturation. But denaturation can also affect the secondary and quaternary structures, but the key one is the tertiary structure. Because the tertiary structure is what maintains the shape of the active site, which allows the interaction. I've avoided that sound for a while. Moving on, you've got that slide. You don't need me to read through all those points, do you? I'm quite capable of reading. Enzyme action. You can have your lock and key, you can have your induced fit, or your coenzyme effect. The coenzymes are fascinating thing in its own way. It's like there's this protein just waiting around it wants to be an enzyme, but it just needs a bit more to get it going. So you need usually a vitamin or a metal ion which comes to the substance. Now basically, you need to be aware of the different structure. Now the induced fit, it has that nice little interaction where the substrate, that interaction can cause the active site to change enough to allow it to fit. But of course, the active site goes back to its normal shape if the substrate's not there. So the induced fit is it's not sort of done as heavily as the lock and key model, which is the obvious model. So basically the enzyme is only specific, and that's where your chiral carbons come in. Because those non-superimposable mirror images, the enantiomers, if one enantiomer is going to act as an enzyme, the other one is not. Because it won't have the ability to fit the active site. So basically that's where the chiral carbon link to enzymes comes in. And that can be really, it's not only useful in enzymes, it's also useful in reactions throughout the body. It may be that often drugs are just one enantiomer of a pair of non-superimposable mirror images or geometric isomers. And that only one of the drugs is effective. The other one may actually be dangerous because of the way it interacts with the body or when it interacts with molecules in the body. So enzymes are chiral, react with specific enantiomers of chiral substrates. If one enantiomer actually interacts successfully, the other one ain't going to, usually. Now just a little bit, see I got a bit carried away with coenzymes because of Vegemite. When I was preparing this, I read an article. The heading was Australian scientists pioneer Vegemite breakthrough that could prevent thousands of miscarriages. They suggested that pregnant women should eat Vegemite. Now, I'm going to come back to this a bit later as well. The idea of the coenzymes are effectively electron carriers. They have an effect particularly in things like respiration with oxidation and reduction. But the idea of a coenzyme is it basically is what makes that apoenzyme, the inactive protein, become active. And the thing that's in Vegemite is niacin or nicotinic acid, which is converted into niacinamide, and that actually becomes NAD+, which is the coenzyme. Now you can read, there's another slide, I'm going to go back to this later, I'll put that slide in for general reading. Not that all of that's going to be assessed on the exam, you certainly don't need to remember the structure of niacin, but you could be asked how niacin could be converted to niacinamide. So basically you've got to turn the carboxyl group into the amide group. More on that later. Amino acids, of course, have zwitterions. Now, zwitterions are basically, there's a certain pH for each amino acid at which the zwitterion exists. They're often not far off 7. But really, a zwitterion is almost like amino acid molecules reactively with each other. It's not as if a proton decides to hop from one end to the other. It's interaction between amino acids. Then, of course, the acidic end becomes basic after it's become protonated. So the basic end becomes acidic after it's become protonated. The acidic end becomes basic after it's been deprotonated. Then you have the effect of pH. At high pH, then you're going to expect either the amino acid or the zwitterion to be deprotonated. And at low pH, you're going to expect there will be at high pH, you're going to expect deprotonation. And at low pH, you're going to expect protonation. In other words, here, the NH2 is going to proton here, the O- is going to proton there. Now, interesting aside, on the zwitterions, side groups are not protonated or deprotonated at that pH. At the pH at which the zwitterion exists, side groups are not affected. So zwitterions always have a charge of 0. But at high pH and low pH, side groups are affected. So for example, at low pH, this amino acid has a charge of +2. That's a little aside there. And of course, pH and temperature dependent enzyme activity. Enzymes work within a narrow pH range. Put them outside that range, they don't work. And so basically they're pH specific. And we know that once we get above around 40 degrees, then your enzyme tertiary structure starts to break down. And so the idea about this, of course, this increase in reaction rate is not due to the active site per se. It's simply that the higher temperature means the molecules have more energy and effectively get to the active site quicker. Sorry, I keep turning my back on ones over there. No, because I'm looking at this. So now we're up to the nasty question. How is the product of digestion of the biomolecules associated with fructose, sucrose, lactose, and all of those oses? I'm sick of the oses, and glycogen and amyloid pectin. Let's run through that, and all of this will be in the solutions. So alpha cellulose, I'll just mention that to start with, and fructose combine to give you sucrose. Galactose and glucose and beta glucose combine to give you lactose. Why have I put those two in? Now, I think the structure of the data book is alpha glucose. So where that be? Basically, all that fundamentally means the difference between alpha and beta is you'll notice how this HOH is effectively flipped. That's probably keeping a simple idea, but I think the only molecule represented in the data book is the alpha glucose. So if you're asked to know about beta glucose, you'd have to be given the information. Maybe given the structure of lactose and asked to deduce the glucose, the structure of glucose from it. Why do I put lactose in? Because it's a logical thing to do but many humans don't have lactase, the enzyme necessary for lactose digestion. It's lactose intolerance. So that's actually just a nice little, and it's also the other link where sucrose and lactose are effectively structural isomers. So there's all sorts of links can be made there. Most of it's common sense in terms of exam questions, most of it's common sense interpretation. But just because the carbohydrate, in this case the disaccharide, is ingested, doesn't mean it's appropriately hydrolyzed. And certainly if you're lactose intolerant, lactose is going nowhere. Then we have sucrose versus aspartame. Now, the difference between sucrose and aspartame, aspartame is going to take us on a bit of a journey here as we do this. So, where are we going? Well, firstly, people often use aspartame as a sugar alternative. They still get the same sweetness factor without basically the energy content, if you like, in terms of the amount they have. Aspartame is over 100 times as sweet. Look at aspartame. Notice the functional groups on aspartame. That's going to be significant in a moment. Now, of course, aspartame, basically OH and NH bonds, give it a good hydrogen bonding link. Why do I put that little bit in? OH is a good hydrogen bond acceptor, CH3 requisite non-polar group. That's how it interacts with your tongue. That's sweetness. And so the triangle of taste. I just threw that in, I thought it was a useful idea. I like question 3A. Sucrose and aspartame have approximately the same energy content. What is it? Would that be a fair exam question? Yes. Because your data book gives you the energy content of carbohydrates and proteins. We can argue that aspartame has a little bit of the protein about it. It's not a protein per se. And of course, sucrose is clearly a carbohydrate. So you might expect 16 to 17 kilojoules per gram. That's just from your data book. Fair question? Who knows? Given they have the same energy content per gram, why is aspartame less fattening? Well, simply, you have far less aspartame. You consume far less aspartame because of its greater energy content. I've tried greater sweetness. Now B. This is my favourite question. I'm going fast. Remember, all of the answers will be in the solution, which I will give you today, once I realise there's no errors in it. So, what you do, I want you to come up with 3 products of the hydrolysis of aspartame, please. You actually have to do something. You can't just get ready to talk all the time. Sorry? Just the data book will help you get the names, but I just really want to know these. Yeah, okay, why not? I presume you haven't done it. That would be a fair exam question, that's it. And it would be a good exam question, because not all the products are amino acids. So that's a good point. Anything that's in the data book is fair game if you're asked to identify. So, you don't have a data book, so I'll help you out. Aspartame, you have, of course, the peptide group and the ester group. So it breaks up into 2 amino acids and methanol. Those amino acids are aspartic, phenylalanine, and of course methanol, non-amino acid. Fair question. Yeah. Structure, breakdown, reasonable question. Now, this is where it gets interesting. Cranking up the difficulty now. Shown on the next slide are IR, remember the structures will be in the solutions if you didn't get them down. IR spectra of one of the products of the hydrolysis of aspartame and IR spectra of 2 compounds into which this product may be converted. Give the structural formula of each of the compounds represented in the spectra. Explain using appropriate equations how that product of hydrolysis may be converted to each of the other 2 compounds. It makes you think. So over the page, we have 3 spectra. I should have told to bring the data books. I should have thought of that. Such is life. So, although I've got some. I have it. I thought I had it there. I do have it. Now, your task is to identify those three spectra, all of which are related to that one product coming from aspartame. And there's a little assistance for you. Excuse me. Sorry. If I cough a lot, don't worry. If I get older, my asthma becomes more problematic. Sorry? No, it's good, mate. Thank you. Now, few clues. If you know your spectrum well enough, you sort of know what that is just by looking at it. Not that that's going to help you on the exam, it looks like. And you know that one sort of by looking at it as well. Depends on how much exposure you've had or how much exposure you've given yourself. But according to our little, to me that looks awfully like OH alcohols and CH. OH alcohols 3200 to 3600 and CH 2850 to 3090. No effective overlap. It's a good way to distinguish between alcohols and acids. Alcohols don't have that significant overlap, acids do. I reckon that's actually methanol. Agreed? Now, what else do we have here? What about this one? Can't remember which one I do second. I'm about to find out. Let's look at this one. Yes. I've got a C double bond O. How do I know it's aldehydes? Well, it can't be a ketone. You can't get a ketone from primary alcohol. So it probably has to be an aldehyde. And you'll notice down here there's no evidence of any OH bundle gains. OH is either going to have that nice smooth characteristic of alcohols or that overlapping characteristic of acids. That's CH. That's got to be methanol HC. Of course, the functional group in methanol is the carbonyl group. It'll be interesting. It'll be interesting on the exam this year, what's accepted there. It is the carbonyl group with an extra 8 with the 8 bonded to the H on the other side, but pass on that for the moment, because I have no idea what they're going to ask on the exam. But the textbook, does the textbook refer to aldehydes or just carbonyl?
It does both. In the text it's aldehyde, but in the glossary it's carbonyl.
Yeah, that's it. That'll be, that's one of those ones. You can't be wrong if you say carbonyl, and at this level you shouldn't be wrong if you say aldehyde, but I don't. That's an unofficial comment. Certainly carbonyl covers all bases. As long as you know the difference between the carbonyl group in an aldehyde versus a ketone, that's probably more the distinction, understanding why they're different. And what about this one? Well, see, if once you've had enough past exposure, well, that's got to be an acid. OH overlapping CH, that's clear. OH clearly overlaps CH, C double bond O, methanoic acid. So reasonable interpretation. And I presume you've done spectra reasonably enough for that to be done. So how can we convert methanol to methanol and methanoic acid? Again, revision point. Basically, oxidise it. Oxidise it. Could you write Bell-Stark equations? I'm sure you could. Methanoic acid. And of course, we get oxidised to the aldehyde. Agreed? Does that make sense? And I should make you. That should be fairly straightforward chemistry with 2 extra hydrogens, 2 electrons, etc. Dichromate. Now dichromate, acidified dichromate, is the reductant. I'm going to visit that later where you do have to write the half equation, so I'll skip through it quickly now. You can oxidise methanol to methanoic acid, but I put permanganate in there. That's a valid alternative, acidified permanganate. Again, you basically should be aware that they're pretty much standard. Oh, whoa, typo. Who can see the typo? Who can see the typo? Anyone? Yes.
Is that like there's 2 carbons in the
Is there enough?
They have, but they haven't picked it. It's the 2 minus of.
And the 2 minuses. My mistake. If that's still in the solutions, please cross it out. I can't remember. MnO4 minus. Typo. Okay. Yes.
The red line is the one part of the
Very good. Very good. Very good. I'll fix that now. Let's do that. Let's balance that. Thank you. That's a classic mistake, that one. So this should be 2. You've seen that CH. Help me out here. What's the rest of it? No, look, basically, that's not the error. The error is here. That should be HCOOH. Is that balanced? How many hydrogens? Is it balanced for hydrogen? Good, thank you.
You want to fix the manganese while you're
That was just a silly error by me. You know, obviously, that's a problem with teaching. Inevitably, in the past, we've almost done ethanoic acid. It's rarely been methanoic, so I just got sucked into that. That looks right now. And that should be a minus.
Change the manganese what you need.
Yes, thank you. As I say, a lot of these are first-time questions, so please forgive the errors in that sense. And I have a feeling I'll try and adjust the solutions if I remember before I send them on. Okay, now let's move back to, it gets more interesting here. Still on the spectroscopy bit for the moment. Now, let's just go to our next slide. Now, here's basically a bit more challenging for you. Read the question. Mass spectrum of compound 1 produced by reacting one of the 2 compounds obtained from methanol with ammonia. 1H NMR spectrum of compound 2, which is isomeric with the compound produced by reacting together one of the compounds obtained from methanol with methanol itself. That's deliberately to get you out of your comfort zone and think. Spectrum 1, produced by reacting one of the 2 compounds obtained from methanol with ammonia. Spectrum 2 is isomeric with the compound obtained when you react one of the compounds from methanol with methanol itself. So you've got to refer back to the previous slide. Now remember, the products on the previous slide were methanol and methanoic acid. Waiting for someone to pick up a potential glitch here. Okay. Did we get methanamide for the first one? Which would be methanoic acid with ammonia. And basically that will give you methanamide, the carboxyl group with basically ammonia. And the other product will be water. Give the formula for the peaks. That's a fairly tough question, by the way. But The peak at 45. What's the peak at 45 going to be on the mass spectrum? Any suggestions? It is the... It's a paradigm, is it? Is it up to 45? It's a paradigm. Why was there no reaction there? The paradigm. What's the peak at 43? The paradigm, less 2 hydrogens. What's the peak at 29? Peak at 29. The mathematical gymnastics here. Anyone? Anyone? HCO. Plus, of course. We put it in square brackets just to the pluses across the whole molecule. That's again just it's a challenge. If the examiner would not be quite as harsh in that sense, but it's making you think. You've done all this stuff, but how much is sort of locked in? If anything, it inspires you to get back into the revision a big way. Name and write a balanced semi-structural formula equation for the reaction with methanol of one of the compounds obtained from methanol. So which of the compounds obtained from methanol is, and remember that's the previous slide, options were methanol or the aldehyde and the acid. So what's going to be write the equation. Write the equation. Actually do it. That means pen in hand, piece of paper, write. It's a wonderfully liberating experience. Of course, it's a production of an ester. Does your equation look like this? Notice the states are all liquid. CH3OH, HCOOH, HCOOCH3 plus H2O. Ring a bell? I'm not sure if there's a look of stun. Have we done that? Yes, you have. Just in the context. This is good. I mean, not everyone's going to it's easy. Part D, identify compound 2 and explain the peaks on its NMR. Identify compound 2. Compound 2, remember, is isomeric with the compound produced from methanol and methanoic acid. And it's got 2 peaks. And it's a proton NMR, which means it has 2 hydrogen environments. And it's isomeric. Anyone got it yet? There's a hydrogen environment down around 11 and a bit, which is awfully like the hydrogen on the oxygen of a carboxyl group. And the answer is ethanoic acid. Acids and esters with the same amount of carbons are isomers. Higher level question. Higher level question. Do you agree? Okay. Now look, for those of you who are thinking, gee, I need a bit more work on spectra, there's a few slides later on which go back a bit, we've got to take it back further. These are challenging questions. You're getting the challenging questions out while your brains are still working. Can we move on? Now you've got that slide as is. Let's move on. Now, oh, by the way, just a little, of course, you've got the 2 singlets talking about the proton NMR. The one at chemical shift 2.0 is the hydrogens on the carbon. The one between 9 and 13 is, of course, the hydrogen on the carboxyl. So again, a nice little reminder of some basics there. Moving on. Now we get back to a little bit of quick read of the question, please. Quick read of the question. process does that reaction occur? You're starting with a fat triglyceride and ending up with an ester, a fatty acid ester, which suggests it is biodiesel. Fairly standard procedure. Biodiesel is produced, again, difficult to know exactly how much you need to know. This is produced by transesterification. To get the COOCH3, you actually have to get a reaction occurring in here, which is effectively a breakup of the ester group. And the direct reaction is actually with the alcohol. The alcohol used must be methanol, because you end up with a methyl fatty acid or a methyl ester. The other product of the breakdown of the fat is always glycerol. So you actually must have 3 methanol molecules. If it was an ethyl ester, it would be ethanol. So effectively in the transesterification, you get reaction of the alcohol across the ester group. You could actually break it up into 2 parts, with water reacting to give you the fatty acid, and then the fatty acid reacting with the alcohol. So that's basically the production of biodiesel, triglyceride and alcohol. The products of the reaction, again the data book will help. That's given in your data book. The fatty acid is given in your data book, and the answers are methyl stearate and glycerol. If the ester product was methyl linoleate rather than methyl stearate, how would its melting temperature compare with the ester product of this reaction? So in other words, if it was linoleic acid rather than stearic acid, how would it affect the melting temperature? And also things like viscosity and cloud points. So methyl linoleate has clearly got the Kink structure because of the carbon-carbon double bonds. The molecule's not going to pack together as well. So that's going to mean that you would expect it to have a much lower melting temperature and presumably a lower viscosity. How does biodiesel have a higher viscosity and higher cloud point than petrodiesel? Now, basically, petrodiesel, that's just hydrocarbons, mainly alkanes, mainly straight chain. So basically, fatty acid esters are bigger than alkanes though. And why do they so if we talk about this biodiesel, you've got that nice simple structure, but even with biodiesel tends to go from about 9 to 16 carbons. They're not massive molecules. Fatty acid molecules tend to be much bigger. But also fatty acid molecules don't only have, the biodiesel molecules don't only have dispersion force attraction, they also have some dipole-dipole attraction due to that CO double bond, which is polar in its own way. So there is that little bit of extra stuff there. All of that, as it says, are in your solutions. I hope those answers as such. I'm depending on you to let me know if there's anything there that's wrong. You're happy so far. Good. And it's a nice little, the biodiesel versus petrodiesel, they're nice esoteric things. Things like viscosity, cloud point, flash point, etc. Some more on that later. Moving on. So yes. Oh, yeah, that's the typo. It should be higher. High viscosity, yes. Is that lower and lower on yours? Okay. Oh, check what's on the screen. That's correct. Well picked up. Should be higher. Can't have a lower viscosity and a higher cloud point. Okay, now, a bit more work for you. Can you actually write that balanced equation, just in case you need the formula that you've got the ester on the previous page? Actually write the equation. Actually do it. You've got to do some things to keep your mind ticking over.
Chris, on the formation, would you ever be asked for states? I mean, I'm assuming we're going to put some states in here.
Yes, basically they pretty much the biodiesel tends to be But I see where you're going, you probably get the states of the products.
Yeah.
I'll get to that. Good point. Yeah, biodiesel darling, so it's an open question like this. I think you've got a choice in terms of that product. The question under that is far more specific. How are we going on this balancing with the equation? Would you work out the molecular formula or whatever you want to do with the fatty acid under Yester? 1938-2. Adding up the carbons, the hydrogens and the oxygens. We're going now, I've done 6 questions. There's every one of them. We're doing about the first 10, then we're going to pick and choose. So, remember the balancing the equation. Carbon, hydrogen, oxygen, but don't forget to discount the oxygens in the fuel. So does your balanced equation look like? What's the slow development? How many carbons on the left? 19. Hence you have 19 CO2s. How many hydrogens on the left? 38. Hence you have 19 H2Os. Total oxygens on the right, 38 plus 19 is 57. Subtract 2, there's 2 in the fuel. You need 55, which is 27.5 oxygen molecules. Now, notice all the states are liquid, gas, gas and liquid. Now, there's no argument to say with that equation you couldn't have gas for water. You're not given any specific conditions. And it may be at the temperature gas for water is more realistic. When you write the balanced equation for complete combustion of methanol, so we've done methanol, write that one as well, please. Complete combustion of methanol should be a very quick one. Excuse me. So, fairly straightforward. Methanol, oxygen, 1 CO2. Now, we have 2 waters. Total oxygens on the right-hand side, 4. 1 in the fuel, subtract that, this gives us 1.502 or 302. Now, if you're asked to write the balanced thermochemical equation, to the data book, and get the delta H. Now this is very important. You cannot have H2O gas in that equation because the delta H values in the data book are quoted at 25 degrees C. Just one of those little fine-tuning things. A general combustion equation, I have no problem with H2O gas. A specific thermochemical equation, I do. 1.2 gram of methanol was consumed in heating 250 grams of water by 4.6 degrees. What percentage of the energy released by the methanol was transferred to the water? Hang on, what's that old water, heating water specific heat, ring a bell? 1.2 grams of methanol, data book helps you out. According to the data book, methanol has an energy content of 22.7 kilojoules per gram. So you know the energy from the methanol. 1.2 by 22.7. What about how much went into the water? Specific heat, 4.18 by mass of water, volume of water times change in temperature. Should work out at 4.18 by 10 to the 3. And therefore the percentage energy into water divided by energy from methanol, 22%. I think that's mathematically correct. So again, that's just a reminder, and that wouldn't be a bad question on an exam. You get a little bit of specific heat, make sure you use the data book. Nice, relatively straightforward question. Not very efficient, mind you. Assuming natural gas is a mixture of methane and ethane, determine the percentage by mass of ethane in the mixture. You need some stuff from the data book. It tells you methane has that as its energy content, ethane, and natural gas. Now, I think this is a higher level question as well. According to that, how can you work out the percentage by mass of ethane in the question? Well, let's assume that the fraction of ethane is X, which means the fraction of methane will be 1 minus X. If you want to use percentages, use 100 minus X. Then it's just 51.9 ethane times the amount of, times X, 55.6 methane times 1 minus X. That should give you natural gas, 54, and then do the maths. And I'll just get the math through fairly quickly, should work out at 43%. Again, it's not important, you sort of, it's just the idea. So yeah, that would be a nice different question, reasonable question. Of course, it'd be a nice multiple choice question where only one alternative was less than 50%. And that has to be the answer because natural gas, its heat of combustion, is actually much closer to methane than ethane, which means you must have more methane than ethane. So there's many ways of asking that question. Okay, quick mental check. How do you convert ethane and ethene to ethanol? What do you need? This is how much have you remembered? Right. Anyone help me out? Ethane to ethanol, 2 steps. And chlorine and? Yeah, and? OH minus. Chlorine, OH minus. Get a lot more on that later. And of course, ethene, that's a substitution reaction. Ethene is directly with water, ring a bell? Ethene with water going to ethanol. Okay, where are we going from here? Again, I'm not stressed about you've got me all that down because it's all on the slide. This takes it to a slightly different twist now. Suddenly equilibrium decides to come apart. We'll have a break soon. We'll be going an hour and a quarter, would you believe? Let's do this question now. Now I want you to do the first 3 parts of this question. I want you to do it, please. Actually do it. Part A is no problem. Part B should not be a problem, and Part C is interesting. Part D is surprising. I thought it was photocopied in colour. Oh, sorry, I thought they had black and white.
Blew the budget out, mate.
Oh, no, I'm glad I didn't spend any time on those. How we going? We just wrote the previous equation. You should be able to write an equation for ethanol from ethane. Now I want you to work out the delta H. And then a little bit of a discussion. The equation, hopefully you've got ethanol plus steam, phosphoric acid catalyst, sorry, plus steam, phosphoric acid catalyst. Don't need to put the catalyst in this per se. It's an equilibrium reaction. If you don't have equilibrium arrows, no marks. If you're told it's an equilibrium, you must have equilibrium arrows. There is no option. You can't have, alkanes don't react well directly with something. You have to go right before. It is possible to use all sorts of alkanes you have to go by before alkanes get to the alcohol. Alkenes direct. So, how are we going to work out the delta H? Well, we've got 5.10 kilograms of ethanol. Therefore, you should be able to work out the number of moles, mass divided by molar mass. Make sure you convert the mass to grams. And then, the energy released per mole, we're told 5.01 kilograms releases 5.01 megajoules. So I've worked it out in megajoules per mole. Delta enthalpies tend to be given in kilojoules. So 0.0451 megajoules is 45.1 kilojoules. There's 1,000 kilojoules in a megajoule. And you're told it releases energy, so it's exothermic, which you need the negative. Now, the next question, why does the production of ethanol, why is it favoured by high pressures? And how does increasing the pressure lead to a higher percentage yield of ethanol? There's two parts to that question. Why and how? Think about it for a moment. Why and how? Why is Le Chatelier? You increase the pressure, the system will try to partially compensate by decreasing the pressure, favouring the side with fewer particles. There's your why. But how? Le Chatelier tells us why it happens. It doesn't tell us how it happens. I mean, here's a reaction trundling along happily in equilibrium. You increase the pressure and suddenly it decides to go forward. What does that tell you about another impact of the increase in pressure? If the forward reaction is favoured, its rate must be faster than the reverse. So the implication there, why is because it favours the side with fewer particles. How is that the increase in pressure must increase the rate of the forward reaction more than the rate of the reverse reaction. A system can't move from equilibrium unless there's a disparity in reaction rates. And it's clear here, you must have an increase in the rate of a greater increase in the rate of the forward reaction. So a nice little bit of organic chemistry, bit of equilibrium, link it together, bit of delta H. The ester produced has the lowest boiling point of all the species in the equation, despite having the largest molecules. These are the boiling points, by the way. The ester has the lowest boiling point. Is there a simple explanation for that? All the others have hydrogen bonding. The ester doesn't have hydrogen bonding. So even its bigger molecule and its greater dispersion force, that's just a little hydrogen. I threw that in to make life entertaining. Okay, just a little bit more before our first break. Happy with that? You've got exactly that slide in your solutions. Now, of course, we've already done part A, combustion of ethanol. I'll stick that equation in. if you want to do it yourself, don't write it in now. Go back when you look at the answers and do it. And the thermochemical equation from the data. That's logic. Okay, we've got products and reactants. So that means if you want to fit this to the energy profile, that's what it looks like. That's what it looks like. To get that 1360 kilojoules per mole, you must have 1 mole of ethanol, 3 moles of oxygen, 2 of CO2 and 3 of water. Then we come to the obvious question. Why does a catalyst have no effect on the delta H value? What's the simplest answer to that? Why does a catalyst have no effect on the delta H value? Sorry? Yeah, I don't think that sort of shows enough. It's valid, but it's not exactly what I'm after. And the change in enthalpy is the same because it doesn't affect the energy content of the reactants or the products. It doesn't affect that. So that's why the change, it does have an effect. We know it lowers the activation energy, but it doesn't change these relative positions. We know it increases the rate by lowering the activation energy, which is never enough to get you a mark on an exam these days. You need to have the consequence of that, lowering the activation energy via the alternative reaction pathway, increasing the proportion of successful collisions. You're unlikely to get a mark these days for saying catalyst loss activation energy. We can teach you year 7 that. There's that little bit of the implication of that. Has no effect on the relative energies of reactants and products, no effect on positional equilibrium. I think I've got that slide in there, but just to be safe, if you need to copy that down, perhaps you should. It doesn't have a question number on it. So, again, delta H's, energy profiles. How do we deal with energy profiles on exams? Right, you can be asked to draw one, you'll be given energy content, etc. Lots of options, or you could do question 8. So question 8, I'll go back to the previous slide. I want you to actually do question 8. You're going to earn your first grade. Actually read it quickly and have a go at it. It's off a past exam. It's a nice way of checking some understanding of energy profiles. First part, you've got to write the equation. Well, probably you add step 1 to step 2. Which step involves an endothermic reaction? Provide a reason which step is slower, justify your answer. Now you look at exam style material here. The equations just added together, looks like that. Basically, you cancel out your CH3 3C pluses. Oh, does that sort of bring anything to mind, that formula? Anything you've studied this year? Anything about alcohols? It's one of those tertiary alcohols. Tertiary alcohol. You got that. I didn't see that. We'll get back to that in a moment. Okay. Which step is endothermic? If you get this wrong, I think your teachers will disown you. Clearly, it's the step on the left. What's your reason? What's your reason? Energy's been added. Products have a higher energy content than reactants. I like that one. Energy has been added is a sort of a nebulous answer. Yeah, endothermic reactions have energy added. We know that. But the reason it's endothermic is the energy content of the products is higher than the energy content of reactants. Again, it doesn't hurt to have that better quality response. Which step is slower? Oh, why don't I use that microphone so I don't have to strain my voice so much? I'll learn my lesson soon. Which step is slower? Justify your answer. Which step is slower? Any suggestions? Step 1, I agree. Why? Higher activation energy. So, remember, the activation energy is the energy needed to break the bonds, get up to the top of the curve, etc. You would expect at a certain temperature, a higher activation energy is going to make the reaction more difficult. So basically, higher activation energy, small proportion, I think basically the higher activation energy is nothing. You could say the consequence, a smaller proportion, at a particular temperature, you'll have less successful collisions if it's got a higher activation. I could have worded that better. That's saying a particular temperature, the reaction with the higher activation energy will have less successful collisions. Remember this, I mentioned before, quick bit of naming. God, you're out to earn your first grade. Quick bit of naming. Which gives it all? You're too old right there. Two methyl. And this is the last slide before our break. Number 1, number 2, number 3, number 4. The 4 isomers with 4 carbons alcohols. Yes, you do have to be able to name those. Also, primary, secondary, tertiary. Agreed? And a little bit of chemistry. You can go to the aldehyde to the acid. You can go to the aldehyde to the acid. You can go to the ketone or the tertiary alcohol. We'll pick that up. Let's have a break. 15 minutes max. We'll do an hour and a half. Please be back here within 15 minutes. Yeah.